we have a critical mass, so we can start. Maybe I should give you some more light this time around. Oh, but you have enough light, right? I wanted to do this in review problems, which you would hopefully be able to solve yourselves, ideally. Don't be scared. Because we have covered all the important theory, so now we just need to review it and tie a couple loose ends, so you are all set for the final exam. That's the thing. By the way, if you have something that you would want me to review on Monday, that's the last class, right? On Monday, something specific that like didn't come out so clearly as it could have, then tell me. I can adjust the schedule on Monday accordingly, or I can just give it some thought.
Is the final exam comprehensive from the beginning, or?
That's a good question. I mean, even in these examples, it's sort of sometimes it's hard to tease apart what exactly piece of linear algebra is it using. It'll be mostly steered towards the second part of the things that were not covered in the midterm. But I cannot guarantee that you will not need some knowledge over there, because it's like logically building on top of one of the
Will there be a practice posted?
No, I'm instead gonna do some practice problems right here. Yeah, I don't have a formal practice thing. I mean, you have done a bunch of practice by now, like by yourselves.
Yeah, I guess just to see if there's any particular format, but it's just.
Oh, the format is the same like you have seen before. The midterm, all the homeworks, just basically examples you need to solve. It will be less computation heavy, less algebra heavy, so that you cannot do so many mistakes by like doing long derivations, like computing 2 times 3 minus 7 plus 2 and so on. So there won't be that much. I mean, a little bit of that, but not as much as was in the midterm. So it'll be more about remembering the facts and being able to connect them together and apply some logic. Okay. So we can start. Oh yeah, and as you are here, I was also gonna say that I will need TAs for next year. Will be again in the fall, ES 205, and you guys that are here would be good candidates for the TAs. So if you are interested, drop me an email. I mean, it's long-term planning, but it's good to do it already. I mean, you don't have to sign up for it. You just need to tell me that you would be interested in TAing this class for next year. I mean, you guys that hang around here and interact, you would be perfect candidates. So, yeah. That's right. Yes, 6 to 8, I believe. If they haven't changed it, it's really this decentralized planning. I have nothing to do with the scheduling of that.
Oh, is your location? Yeah.
Oh, that's a good question. I don't know. I'll take a note of that. Or should be. Yeah, it's even more funny that I unfortunately won't be here because I have my doctor's appointments in Prague. During that week, that's the only time I could do it. I'm sorry about that, but Tia should be. Shao will do it. She'll be fine. I will be online if you need something. So we will figure out the location. Yeah, that's a good question. All right. So shall we do some practice problems now? So here is an easy one. So there will be some of these true false, right, that you need to decide if the thing is true or false. So one problem is true false. Every permutation is an orthogonal matrix.
Our exam is 308. It's now 303.
Oh, it's already there? 303?
Yeah.
Oh, okay. So the time down 303, 6 to 8, probably PM, right?
Yeah.
And it's on December 19th, right? I think it's what is it?
Thursday.
Oh, it's a weird day like that. Yeah, it's Thursday. Oh wow, that's quite a few of you here. That's cool. Okay, so first practice problem. We will. I just thought we would just do them here interactively. So decide if this is true or false. Every permutation is an orthogonal matrix. So I'll let you think about it for a little bit. Like sort of let's think we are simulating the exam. Does this work? Yeah, that's work. So there are only two possibilities. Can it be true or false? Yes, it is true. That is easy. And what would be the argument? Okay, so okay, we can start.
Well, in every column, there's just going to be one element, and in every row and column, there's one element. So
And that element, and what is that element? What is?
It's like it's the arrangement.
Yeah, you need to recall the definition of a permutation matrix, right? And every row there is all zeros except for 1, 1.
Right.
Right.
So something else would be a linear combination, not a permutation.
What's that?
If you had anything other than ones with zeros, and if it wasn't orthogonal, then it would be some sort of linear combination of those. Something.
I'm not sure I understand that argument. If it wasn't orthogonal.
Because if you're like 0, 0, 2, 0, 3, then suddenly you're adding rows together and it's not a permutation.
Oh, okay. But you were gonna say something?
Yeah, I was going to say the same kind of thing, that because it's like only one element in each column,
Mm-hmm.
you know that no other column can be a linear combination of any other column.
Right.
So you know that all the columns must be orthogonal.
That's right. Yeah. I mean, the argument I was gonna say that by definition of the permutation matrix, if there is one in one row, as I showed it here, then every other row must have zeros there, right? So of course, if you do when you do the multiplication, then this will just be all zeros, right? And the length of every row and equivalent for every column is 1. So that's, you could even say orthonormal matrix. Some people just say orthogonal and they already mean orthonormal. It's slightly confusing. I will try to make it very explicit in the exam. So, but every permutation matrix is orthogonal and the columns and rows have length 1, right? So that's.
Are they orthogonal also or no?
Yes. Yeah, of course. Like look at it, right? That's definitely length 1. So what you need to do to be able to solve easily and quickly problems like this, to remember the definition. What is the definition of a permutation matrix? What is the definition of an orthogonal matrix? And then just reason a little bit about it, and you immediately see that is the same thing. Okay, that's an easy one. So another fairly easy one. So what is the determinant of minus identity? So don't yell the answer yet. Let's everybody think about it for a second. So determinant of identity. You can just yell determinant of identity, right? That's trivial. That's 1, right? And how about determinant of minus identity?
Also no.
It varies.
Is it 1 or negative 1?
That's right. Yeah. Well, try to be think about it and be certain about the answer.
If the dimension n is even, it's 1, and if it's odd, it's negative 1?
Correct. Yes. You can also say it's -1 to n. So the first thing you need to realize in a problem like this, that this is a square matrix, right? So it's an n by n matrix. And it's a diagonal matrix that looks like this. And we know that for diagonal matrices, the determinant is just the product of all these guys. So exactly as you said, if there is an even number of them, it will be +1. If there's an odd number of them, it will be -1. So just the compact version of proving the answer is -1 to n. That is correct. So let's do one more simple one, just to warm up, just for warm up. So here we want to prove that the determinant of inverse matrix is the inverse of the determinant. So again, what is implied here is that A is n by n square matrix, and it's invertible. That's the assumption. So think about it for a little bit. And by proof, I mean do the simple step of logical elementary reasons why that is true. The proofs should usually be elegant. It's not like you would need to like recall like single value decomposition or something like that. Try not to use like some sort of advanced theorem for something that's like basic. So what you want to do here is to recall the properties of the determinant, right? So does somebody want to write it here? Do you want to try my setup? It's sort of fun. No. Okay. Yeah.
A times A inverse is 1, right?
That is of course true. Yeah, that's the definition of the inverse. That's correct. That's one fact you need to recall. And there is another fact of the determinant, right? Which will then really give you this answer. Let's try someone else. I want to give everybody a chance.
Is there a property that the determinant of A times B is equal to the determinant of A times the determinant?
That's exactly right. So that's the second key fact, right? So the first one, as you said, I sort of like this theme effort. So that A inverse is identity, right? And then there is the second property, right? And then all I need to do is put them together. Does somebody want to write it here? And the thing we just said in the previous example, which is trivial, that the determinant of identity is 1, right? Yep.
So, I mean, if you multiply both sides of the equation by the determinant of A, like the initial.
Multiply both sides of equation by the.
So if you take determinant A inverse and equals 1 over determinant A,
Mm-hmm.
and you multiply both sides by determinant of A.
Right. So I will get. So you're like starting from this. So this is what you meant, right?
Right, and then determinant of A inverse and determinant of A can be rewritten as determinant of A inverse. Yeah.
That is 1, right? We know that this is also equal to determinant identity. But do you see sort of what is the problem here? That here, that's actually good that we did it this way, right? Because what we need to do, we need to invert the process, right? Here we sort of started from what we want to get, and then we like build our way up to elementary facts. Like the proof need to work the other way around. It needs to start from the elementary facts, which we trust, and then build our way towards the fact we want to get, right? So this is absolutely right, but then we need to like flip our reasoning. Yeah, Maya?
So if you start from A times the inverse of A equals I with the determinant of both sides?
Exactly, yeah. So if the matrix is the same, then clearly their determinants must be the same, right? So this is determinant of I, aka 1, right? And then this is, by that rule, determinant of A and determinant of A inverse, right? I assume that A is invertible, so then I can divide this thing. Okay, let me write it nicely. So this is that A inverse equals 1, and then from it's trivial, right? I just divide by the determinant of A, which I can because I assumed it's invertible, and that's it. So this is the proof, right? Like right here. Or like a nice way to write it down would be like using these elementary facts, we derive this bum bum bum, and this is what we wanted to show, and you can put a little square there. And that's a beautiful proof. All right. So let's move on to positive definiteness. This I wanted to recap carefully. That's there's a little bit more things. So let's recall what it means for a matrix to be positive definite. So first of all, I have a matrix which is square and symmetric, and then What is the definition of A being positive definite? So first thing I would like you to do is to recall the definition. So I have a matrix. I know I tell you that the matrix is square and symmetric, and I want you to tell me the definition. What does it mean for a matrix to be positive definite? I guess really big part of this business is remembering the definitions exactly. Yeah, Victor? You're Victor, right?
This,
Oh, Vincent.
sorry. Positive definite matrix has eigenvalues that are all real and positive.
So, sorry, say it again.
A has eigenvalues that are all real and positive.
They are all real and positive.
They're
Yep.
strictly positive.
Strictly positive. Yeah, that's what I meant by positive. Yeah. So we're gonna say that all eigenvalues lambda are positive. Yes, that's absolutely correct. One thing we should realize is that the matrix does not have any complex eigenvalues, right? Because if it had, you know that in general eigenvalues could be complex, right? Then what does it mean for a complex number to be positive? I don't know, right? But fortunately we don't have to worry about it because the matrix is real and symmetric. So what we know about the eigenvalues? They cannot be complex. They will be all reals. So this little problem does not appear there. So we know from the fact that the matrix is real and symmetric that all the eigenvalues must be real, and therefore it makes sense about talking about a real positive number, really. For a complex number, it's not so clear what is a positive complex number, right? So that's one definition. There is another definition, which is actually equivalent to it. Can somebody think about an alternative definition for positive definiteness? Or, let's say, criterion. Yeah, that's a good point. So diagonalizable. Well, all I need for diagonalization is this, right?
Yeah.
If I have this, I can already diagonalize, right? And this, so this means that the first property means that I can diagonalize with the diagonal matrix being positive. Strictly. I mean, on the diagonal, of course. There are zeros off diagonal. So what is another? Or you can look as a property of positive definite matrices. Remember when we talked about these quadratic forms in the business?
Oh, the characteristic polynomial.
Characteristic polynomial has to do with eigenvalues again, right? So let me see. What if I wanted to define positive definiteness without ever talking about eigenvalues? Like imagine you're like in my situation and we are talking about positive definite matrix, but I haven't covered eigenvalues and eigenvectors yet, and I want to define what a positive definite matrix is. So I can just, so let's do this. So I will just write it and then we'll prove that it's equivalent, right? You have seen this before. So the other definition is that for every x, the quadratic form is positive, except for for each x is different from 0 to be because for 0 of course it's 0, so I couldn't be strictly positive there, but that's the only exception, right? So now I claim those are two equivalent definitions of a symmetric matrix being positive definite. So what we want to do is to prove that they are equivalent. Prove that the definition 1 is equivalent to the definition 2. So that could be another problem in your test. So first of all, what does it mean to prove equivalence? So we need to prove that one implies 2, and then 2 implies 1, right? What do I mean by implies? So the first direction is if I have a matrix, so this is always there, right? If I have a matrix that's symmetric and has all eigenvalues that are positive, then I need to prove from this that if I take a non-zero x, I will always have this positive quadratic form. That the xtax always will be positive. That's what I need to derive from these assumptions, right? And the other way around, it means that if I assume that I have a symmetric matrix A, and for every non-zero x this is true, then from this I need to derive that all the eigenvalues are positive. Okay? Yep.
So for the first direction, you can write like the definition of the eigenvalues and then the eigenvector. So you have ax equal to lambda.
Yeah, okay, let's first give everybody a second. Think about that. We're already seeing you were talking about the 1 implies 2.
Yeah.
Right. So let's talk about how do we prove that 1 implies 2. Okay, so you can go ahead.
So it's basically you can just derive it from the definition of eigenvalues and eigenvectors. So you have ax equals to lambda x.
Okay.
And because the matrix has symmetric, you can multiply. You can multiply both sides of the equation by x transpose.
That's correct. Yeah. So let me go a little bit slower here. So I assume that all eigenvalues are positive, right? For eigenvalues, this is always true, right? So I can do x transpose ax. Is that what you were suggesting?
Yep.
Plus xt.
And then x is just 1.
If it was norm 1, yeah, or its length x squared, right? Which would be something positive, right? Because eigenvectors cannot have norm 0. So that then proves that xtax clearly, and because we now assume that lambda is greater than 0, right? Then of course then xtax is also greater than 0. So this is fine, except that we didn't really quite prove it for every possible x, right? This way. We only right now we only proved it for the eigenvectors of A. Right? And what we need to do, we have to prove it for every non-zero x. Actually, that's what I should have said here. It must be strictly positive because here we assume that the x is non-zero, right? So yeah, for eigenvector x, this is true. So what about all the different x? Well, how about an arbitrary non-zero x? What can we do there? It's interesting that when I was thinking about it, I also forgot about this subtlety. Does everybody see? We are proving that the first definition implies the second one. So we assume we have a square symmetric matrix which has positive eigenvalues, and of course, because it's real symmetric matrix, it has a full set of eigenvectors, x, right? And every single one of them satisfies this equation. From this equation, we can clearly see that the product xtax must be positive for eigenvectors, right? And if I have some, so maybe I shouldn't have really called this x, maybe I should have called it y being an eigenvector. And if I have a general, I'm given an x, and all I know about x, that x is not 0. Right? So what can I do about that? which I don't know myself. I forgot about this detail, so I have to find out. So I'll let you think about it. I'll also think about it.
Since the eigenvalues of A are linearly independent,
Yes.
you can write X into Y as a combination.
Yes. I think that's a great idea. Okay, let's see if this will go somewhere. So you are suggesting to write X as a linear combination of my eigenvectors, which I can, for a square symmetric matrix, I can totally do that, right? Because you're completely right that the eigenvectors are linearly independent. So for every X, I can write these lambdas, and at least one of them must be non-zero, right? Because X was non-zero, so that's cool. And the question is, I think I know how to finish the proof. Now let's see. That was a good idea. Do you know how to continue from there?
So if the matrix have full eigenvalues, doesn't that mean that all the eigenvectors span the entire space of the matrix?
Yeah, that's what we meant by this. That arbitrary vector X you can write as a linear combination of these eigenvectors. So here I assume that the y1 to yn are all eigenvectors of
so
A.
if it spans it, doesn't that define all vectors within the space of the matrix?
It does, yeah? Or what do you mean all vectors in the space of the matrix?
Yeah, so doesn't that like satisfy the requirements for all x that are non-zero?
But how? You need to somehow justify that, right? We still need to prove that xtax would be greater than 0, right?
Right.
So we can just plug in that expression and see what we get.
So we know all the eigenvalues are greater than 0.
Mm-hmm.
So we just have to say something about all the eigenvectors in order to show that xtax is greater than 0.
Right.
'Cause we really need to, it's that step where the magnitude squared of y is greater than 0. That's what we have to, that's what's getting us right now. If we can prove that
Magnitude
so
squared of
to-
x.
of y in our original proof.
You mean this? Yeah.
Oh no, wait, no, never mind. It's not an eigenvalue.
Yeah, for the
Yeah.
general x, that's not going to be
Yeah.
true, right? I mean, we have something else for the x, right? We know that for... I'm just thinking that the proof must be simpler than this, that we are making it more complicated than it has to be. But that's okay, right? More complicated than necessary proof is still valid. So we can do this, right? That would be true. And we can get the proof from this, but I feel it's a little bit more complicated than that needs to be, because then we can do this, right? And do y1, oops, sorry, lambda 1 y1 transpose plus lambda n yn transpose, and here we have all these funny squares. Now then, what that's going to be? They are all orthonormal, right? Not only that they are linearly independent, but they are orthonormal. So this will be lambda 1 cubed, the norm of y1 squared, and then the terms like this, y1t, y2, they have to be 0, because the eigenvectors of a real symmetric matrix are orthonormal. I don't know why the cubes come out of there, but it's okay. It's gonna be fine, because then this clearly has to be greater than 0, right? Because if I write it like this, I know that lambdas, all the lambdas are positive, right? So this, and that all these are ones, so that clearly is bigger than 0. I just think that the proof should be simpler than that. Let me think about it for a second. Oh yeah, here is one way how we could make the proof easier actually. We could say that we can recall the spectral theorem and factorize A this way, right? So then I know that the S is a diagonal matrix with lambda 1 to lambda n, and those all are positive, right? That's my assumption here, that all the eigenvalues are positive. And now what I need to do is to show that xt q s qt x is positive, right? Because this is just A written in a different way. But then I can just say that xtq is just yt, right? So this thing becomes xtq s qt x becomes yt s y, right? Which is just the sum of my lambda I times yi squared, right? From 1 to n, which again must be positive. So that's like a shorter way of doing exactly the same thing. Does it make sense? Looking at it suspiciously. I think it's fine, right? You can do the spectral decomposition theorem, where Q is the matrix that stacks these y's, right? This is essentially a more elegant way of writing this whole thing. So the Q is the matrix that stacks the eigenvectors. For real symmetric matrix, it always does exist, so that's fine. And then I need to prove that xtax is positive. Well, if I plug it in here and I just say that xtq is y transpose, then must be positive. You have done this before, right? Some lecture, but it's sort of funny. Like it's not the same as like seeing a lecture. Like yeah, totally makes sense. But when you like have to like redo it by yourselves and don't remember how exactly it was done previously, that's when the interest. Then when you really have to think about it. So how about the opposite implication? So if I tell you that I have a symmetric, square symmetric A, and for every non-zero x, this is true, the number 2 is true, xtax is positive, then from this I want to show that all eigenvalues are positive. I think the second one is going to be simpler. So let's think about that for a second. Yeah, that's actually simpler. Someone else wants to give it a shot? I know why I got confused, because here we set it in a different order than I was writing it down. the same thing. Yeah. But let's give someone else a chance now to speak up. Oh, you wanna say it?
Yeah, I haven't completely worked through it, but we'll see where this goes. You know that for all x, xtax is greater than 0.
Mm-hmm.
So, which means that for the x's that are eigenvectors,
Let's write it down. Yeah. So for the x's that are eigenvectors, this is true, right? With some eigenvalue lambda.
and so now we have xtax is greater than 0.
That is
We
true.
can substitute in lambda x.
Okay. Let's see. So you are saying that we can just plug here lambda x. Yeah, that's perfectly fine. Why not? X. So we will get xtx lambda greater than 0, right? Wait, there is no t. Okay, I will write it nicer. How about this? Well, and then you're almost there.
Well, and we know that if it's squared, that has to be greater than 0.
That's right. And
So therefore,
what if it was 0?
it can't be.
That's right. It can be because it's eigenvector, right? It's nice how the things nicely click together. So that's strictly positive. Then the lambda has no other chance than to be positive as well. Right? So if we proved from 2, we proved 1. Nice. So now we know these two definitions are exactly equivalent. So what was the deal with negative definite matrices? What would change? Sorry? Less than 0, right? So if I wanted negative definite, I would say lambda is strictly less than 0. What would change in number 2? xtax. That's a dumb question, I guess, but it's also less than 0, right? So that's negative definite. And we had 2 other variations on this idea, right? What was that? For the semi-definite and negative semi-definite, right? So what is the deal with those? Mm-hmm. Yes. So if I wanted to go to semi-definite, I don't want to put it there because then I would invalidate the entire thing. So positive semi-definite would do this. Like if somebody look at the YouTube video from the middle, they would think I'm an idiot that like I positive definite. So I just write it here. So this is positive semi-definite, right? And this would be negative semi-definite. Semi-def and nec semi-def. Okay, so that's this. That's that. And here is an interesting problem. So let's just look at the 2x2 matrix. So let's consider A 2x2 symmetric. So that means that A is just A, B, B, C, right? For A, B, C are some real numbers. So how can I test A for positive definiteness? So somebody gives me a 2x2 matrix, I want to be able to quickly decide if it's positive definite or not. Testing if it's symmetric, that's really easy, right? And just check if this guy is the same as this guy. So I just like assume that they already are the same, because otherwise you just say, well, go away, it's not even symmetric, right? So this is interesting actually. Let's think about it for a bit. If somebody gives us a matrix, or even for a general matrix, how do we come up with a test of positive definiteness? There's one problem I encourage you to think about in preparation for your final. So like from the definition, right, we could, from definition 2 is probably not going to be super helpful. I mean, it can be. You can go either way, right? But the first look, it doesn't look very practical to just try every possible x and then test if this is true, right? So one thing you could totally do would be use the definition number 1, right, and compute the eigenvalues, and then test if the eigenvalues are positive, right? The computing the eigenvalues is slightly annoying. Not super annoying, but you have to solve a quadratic polynomial, then you get the eigenvalues, and then you get the answer. So there is an easier way how that can be done, and that easier way follows from the properties of the eigenvalues. So we will still be using the definition number 1. So we know that it's positive definite if and only if. So now we have only 2 eigenvalues, right? And what we want to do is this, right? That's the test we want to apply, right? So we could just compute the lambdas and say, okay, let's compute them and test if they are both positive. But interestingly enough, we don't really have to compute them because it's a little bit annoying to compute them. So we might be lazy and not want to compute them. The faster way. The time matters, right? At an exam as well as in life. So if you can do it faster, good for you. So we have these interesting properties, which especially for 2x2 matrix are very elegant. What is the determinant of A in terms of the eigenvalues? That is true, and but I said in terms of the eigenvalues.
They're the eigenvalues. What's the word? Multiply together as the determinant.
Yeah, that's right. Everybody recalls this. That was we had this fact. So all these things and facts and theorems, they are your weapons to attack the problems in the final, right? So knowing them is good for you. One of them was saying that the determinant is equal to the product of the eigenvalues. There was another result like this, right? Relating something of the matrix to something of the eigenvalues. Yeah?
The trace.
Trace of A was what?
This out.
Yeah, lambda 1 plus lambda 2, right? In 2x2 matrix, everything is easier. So the determinant of A is, somebody said it already, right? AC minus B squared, right? So that's the product, right? The trace, what is the trace? Well, that's a really stupid question, right? It's just A plus C. Right? Sum of the diagonal elements. That's what the trace is. Oh, one cool thing for arbitrary matrix, one necessary condition that must be true if the matrix is to have any chance at all to be positive definite is just by looking on the diagonal. So if I have an arbitrary matrix, A11, A12, and so on, that would be A22, A21, A22, and so on, and up to some A and N, and A1N, and AN1, and so on. So there is one necessary condition for the matrix to be positive definite, and that's that all the elements on the diagonal, they better be positive, right? Because if I have something negative on the diagonal, like there was like this guy happened to be negative, then all I need to do is to take this vector 0, 1, 0, 0, and here the same thing, right? 0, 1, 0, and I get the A22. Right. So if A22 happened to be negative, here I have a counterexample to the second property. Right. I found a non-zero vector such that xtax is negative. So goodbye positive definiteness. Right. So did you get it? A necessary condition for the matrix to be positive definite is that all the elements on the diagonal have to be positive. It's not sufficient, right? It's just necessary. So not all matrices that have positive diagonal are. Wait, sorry, I think I confused. I said it in the wrong direction. So what was it supposed to be in the right direction?
Necessary but not sufficient.
Right. So that means what?
So I mean, not all matrix that has positives diagonals are positive definite.
That's right, right. That not all of the matrices that have positive diagonal are positive definite. That's right. It's like part of the truth. Okay, so a criterion for a 2x2 matrix. So we know automatically that A must be greater than 0 and C must be greater than 0, right? Otherwise, no way it could be positive definite, right? And we also know that if it's to be positive definite, that the eigenvalues must be both positive, right? So that means that the determinant must also be positive, right? So that means that the AC minus B squared as the determinant of A must be positive. And this already is sufficient, interestingly. Yeah, why is that sufficient? So first of all, if I have A greater than 0 and AC greater than B squared, then of course this already implies that C must be greater than 0 too, right? Because if A is greater than 0, then this is positive, then C must be positive as well, right? And interestingly, these two conditions are already sufficient. So they are necessary, they must be necessary, that's what we established now. And they are also sufficient. So if A is positive and the determinant is positive, then the entire matrix already must be positive definite. Why is that?
Then the determinant is guaranteed to be positive.
It's not sufficient, right? The determinant could also be positive if both lambda 1 and lambda 2 were negative, right? If it was a negative definite matrix. So the determinant could confuse us a little bit. But we have the second rule. We know what the sum of these two guys is, right? So maybe in the interest of time, I will just say it here. So if we know that A is positive and AC is greater than B squared, then from this follows that C is positive, right? And because the trace of A is A plus C, and it's also lambda 1 plus lambda 2, that means that lambda 1 plus lambda 2 is also positive, right? So that means it cannot be the case that they were both negative, right? Because if they were both negative, then lambda 1 plus lambda 2 would be also negative. So that can't be the case. It must be the case that both lambda 1 is positive and lambda 2 is positive. So for general n by n matrices, we can have the similar statement. So, and this is called the Silvester's criterion. I don't think I covered this, so I just wanted to mention it so you know it, because it's sometimes useful. So if I have a matrix which is n by n this time, and it's symmetric, then I can define what is called principal minors. Principal minors. That simply means that if I have the matrix like this, then I take the 1 by 1 top left submatrix. I can take the 2 by 2, so this would be called A1. This would be called, this entire thing would be called A2. There would be another one, it would be called A3. And so on until the whole matrix would be AN equals A equals this entire thing. And the Silvester's criterion says that A is positive definite if and only if for each k the determinant of AK is positive. So that means for each k from 1 to n. So all these submatrices, the 1 by 1 top left submatrix, 2 by 2 top left submatrix, 3 by 3, and so on, they must have positive determinants. Yeah, I must confess I'm not sure if it works both ways, if it's really equivalence or if it's just guaranteeing positive definiteness. I think, yeah.
How familiar with this Silvester's criterion?
Sorry?
How familiar should we be with the
I can't hear.
the principal minors? Like how comfortable should we be
3, so don't.
How comfortable should we be using the principal lines?
How?
Comfortable, like, is that like the chosen method to prove this, or?
I think he's asking, should we use something like this on an exam? Should we use a technique like, I think that's what you're asking.
Yeah.
Yeah, you will probably need only the 2 by 2 case. This is just an n by n case. I just wanted to tell you that this actually does generalize to the general n by n case. There will be something for just 2 by 2 matrices, something like this. Yeah. Interestingly, it does not. The generalization to semi-definite is a little bit trickier for the Sylvester stuff. But yeah, anyway, this I just wanted to mention that so you have a complete picture. All right, so the time is up. So unless you have some more questions, we will continue with this stuff, which is sort of fun on Monday. Yeah.
Are you gonna have practice problems?
Well, these already are the practice problems. I figured we'll just do them interactively like this, rather than everybody doing them by themselves. Yeah.
Would it get some kind of list of the concepts or topics that we expected to know?
Well, that's everything we covered. You don't have to do the Sylvester's criterion, and there won't be the variational stuff the previous 2 lectures. But other than that, like the SVD and the eigenvalues and eigenvectors and determinant and all that stuff that will be there. It will be more steered towards the second half of the course, but again, I cannot guarantee that you wouldn't some knowledge from the first part wouldn't be useful. Yeah, it's like the standard linear algebra stuff, pretty much what the syllabus is.